Hi friends, very good morning. I hope all of you are doing good. Please stay home and stay safe. In this class or in this video, so we'll just understand the Faraday's laws of electromagnetic induction. So Faraday, the scientist named Faraday, conducted his experiment in 18th century, and with that invention we got some basic or some important electrical machines like generators, motors, transformers, induction motors. Like that, we got different electrical machines due to the invention of electromagnetic induction. So this experiment has been done by the Faraday in the 18th century. So it is a very crucial experiment which changed the electrical engineering era, which changed the electrical engineering perspective with the Maxwell, with the Faraday, with the Ørsted. All these are genius scientists who invented these laws like Lenz's law, Maxwell equations, Faraday's experiment, all these right hand thumb rule, all these things. Okay, now in this video we will understand how to perform a Faraday experiment with the help of small components that are available with us. Okay, so we just need some bunch of copper winding, means some 3 to 4 meters or 5 meters of copper winding, and with that we can make two copper coils, and we will see how this electromagnetic induction works between these two coils. Okay, so this is a very important experiment, and we will see that in a practical manner. So with the help of small components that are available in our homes, how can we observe the Faraday's laws of electromagnetic induction, and how the power can be transferred from one circuit to another circuit with the help of small experiment. And we can divide these Faraday's experiments into two types. Okay, basically he conducted with three things, means three observations are made in the Faraday's experiment, but in this video we'll just see two things. One is with when we have two coils, and one coil is supplied with battery. When the coil is supplied with battery, automatically there will be some magnetic flux created. When that magnetic flux trying to link another coil, right? So when you keep first coil and second coil nearer to each other, when one coil got excited, means by giving a DC supply or connecting to a battery, this coil circulates some current. Because of this current, some magnetic field produced, and that magnetic field links with the second coil which is nearer to the first coil, right? So when it links with the coil, the EMF will not be induced, but because there is no change in the magnetic field produced. That's why what Faraday did is he excited one coil, and he moved the second coil near and far away. Like that, he created some relative speed or relative displacement between the first coil and the second coil. When he created some relative speed between the first coil and second coil, automatically there will be change in the magnetic flux, means the magnetic flux linking with the second coil automatically changes. See, when the second coil is far away from the first coil, the magnetic flux linking with the second coil produced by the first coil is very less. When the second coil is coming nearer to the first coil, the magnetic flux linking with the second coil will be increased. So previously the magnetic flux is very lesser. When we move the coil towards the first coil, the magnetic flux change, means increases. So there is a change in magnetic flux created. Due to this change in magnetic flux, there will be an induced EMF which circulates some current in the second coil. Okay, so this is the first experiment which we will see, and in the second experiment what we will see is I kept the first coil and the second coil nearer to each other. I am not moving any coil, and in the first coil, in addition to the battery which is connected to the first coil, I connected a switch, right? So when the switch closes, the battery is connected to the first coil. When the switch opened, the battery is disconnected from the first coil. See, when the battery is connected, it will circulate the current. When the current is circulated, the magnetic flux is created, right? So that magnetic flux links with this second coil, right? So before the switch closes, the magnetic flux linking with the second coil is 0. When the switch closed, then suddenly there will be circulating current in the first coil, so that a magnetic flux created, and that flux links with the second coil. Now the flux changed from 0 to some value, so there is a change in flux. Again, when I opened the switch, the current in this coil got 0. When the current in this coil got 0, the magnetic flux will be 0. So previously the magnetic flux is maximum, now again it is reduced to 0. Like this, by opening and closing the switch which is connected in series to the coil, means from the battery, means in between the battery and the coil I connected a switch. By opening and closing the switch, the current through the coil changes. When the current through the coil changes, automatically the magnetic flux changes, and that flux linking with the second coil creates some EMF. So that flux is a changing flux. So whenever there is a rate of change of flux happening, then there will be an induced EMF created. Okay. So in the first case, I moved, means I created some relative speed between the first coil and second coil. This is the first case. In the second case, I kept the first coil and second coil at its stationary position, and I changed, means I just opened and closed the switch, so that I changed the current. One time it is maximum, then 0, maximum 0. Like that, if the current changes, magnetic flux changes. When the magnetic flux linking with the second coil changes, automatically an induced EMF will be created in the second coil. It will circulate some current. Okay, so the circulating current through the second coil in both the experiments is observed with the help of an LED. Okay, so see, in order to get a sufficient amount of EMF, we need a huge number of turns. As we have a less number of turns, we can see only a small illumination from the LED. So I request all of you to please observe the brightness of the LED in a focused manner, so that you can see its illumination, because it is a very less, because the reason is I have a less number of copper turns. Due to this reason, I can see only a small illumination. Okay, so please carefully observe that and understand. Okay, thank you very much. Now let us have a look on the components that are required to perform the two Faraday's experiments. We'll see one by one. So the first thing, our first component which we require is two copper coils we require. Here I have taken two copper coils with 150 and 100 turns. And the second thing which we require is on-off switch. The purpose of this on-off switch is to make and break the circuit, so as to change the current by which the magnetic field is changed. And the third thing which we require is a 9-volt battery. This acts as a power source or power supply. And the last thing which we require is some connecting wires. First, we'll understand the experiment 1 with the practical setup. Okay, so by switching on and off the power supply, the magnetic field is changed. Here, if you observe, the setup is like this. The positive terminal of the battery is connected to one end of the switch. Another end of the switch is connected to first coil, and the coil, another terminal, is connected to the negative terminal. Like this, a closed path is created to allow the current to the first coil, and this is the second coil to which an LED is connected. Okay, the tape is provided in order to avoid the unwinding. Now what I am doing is I am just closing the switch and opening the switch. I am changing the position of the switch to on and off, so that the current through the first coil changes. I just kept the first coil just above the second coil. I am not moving it, but I am changing the switching position on and off. When I change the switching position, there will be change in current flowing through the first coil, by which the change in magnetic field is created. Hence, it will create an induced EMF in the second coil. right? So as the illumination with the room lighting on is not much, so I have taken a video by switching off the room light, so you can observe this illumination with more clarity when compared to room light on. Okay, so this is about the first experiment. Now let us see the second experiment. The second experiment is creating an induced EMF with a moving coil. Means we are making the relative speed. We are creating some relative speed between the two coils. So I am using the same setup as I have used in the first case. Okay, so the battery, switch and the first coil all are connected in series. When the switch is in on position, there will be some current through the first coil, and the second coil is connected to the LED. So now see, observe, I closed the switch, means I made the switch in on position so that it will circulate some current and it creates a magnetic field around the first coil. Okay, now I am keeping the second coil at a static position and moving the first coil to and fro, means towards the first coil and far away from the first coil. So when I create some relative speed between these two coils, okay, first coil and second coil, there will be change in magnetic field. Because of this change in magnetic field, the induced EMF is created, which circulates the current through LED. Okay, so as the illumination of this LED is very much lesser, in order to observe it, what I have done is I have switched off the room light and observed the illumination. So the bottom box will use this. Okay, see the illumination of an LED because of this change in magnetic field. Okay, so thank you very much.